Somewhere out there, right now, there's a number that scientists agree on. 13.8 billion years. That's the age of the universe. It's printed in textbooks, it's on museum plaques, it's the answer every astrophysics student memorizes. It might be wrong, not wrong by a rounding error, wrong by up to 1 billion years. And the machine that's forcing this reckoning isn't a super collider or a satellite hunting asteroids. It's a telescope sitting 1 million miles from Earth, quietly staring into the deepest, oldest light in existence, and returning answers nobody was ready for. The James Webb Space Telescope was built to look further back in time than any instrument in history. What it found instead is a universe that doesn't behave the way our best models say it should. Galaxies that are too big, too early. Black holes that shouldn't exist yet, but do. And a number, the expansion rate of the universe itself, that refuses to agree with itself no matter how carefully we measure it. This is the story of a universe rewriting its own biography in real time. Stay with me, because by the end of this, the number 13.8 billion is going to feel a lot less solid than it did 5 minutes ago. To understand why JWST has cosmologists uneasy, you have to understand a problem that's been quietly festering for over a decade. It's called the Hubble tension, and it comes down to a simple question. How fast is the universe expanding? There are 2 ways to answer that question, and they use completely different methods. The first method looks backward, almost to the beginning of everything. Scientists study the cosmic microwave background, the faint afterglow left over from roughly 380,000 years after the Big Bang. By analyzing this ancient radiation with the standard model of cosmology, they calculate an expansion rate. Call it the early universe prediction. The second method looks at the universe as it is now. Astronomers measure the distances and speeds of nearby galaxies using stars called Cepheid variables and exploding stars called supernovae. This gives a direct, present-day measurement of expansion. Call it the local universe measurement. Here's the problem. These 2 methods don't agree. The local measurement consistently comes out faster than the early universe prediction. For years, the assumption, or maybe the hope, was that this was a measurement error, bad calibration, a flawed distance ladder, something fixable. UST was supposed to settle this once and for all. It had the resolution and sensitivity to double-check the Hubble Space Telescope's earlier measurements of those Cepheid stars, the ones used to calibrate cosmic distances. If Hubble had made a mistake, Webb would catch it, and the tension would quietly disappear. It didn't disappear. JWST confirmed the faster expansion rate. The discrepancy is real, and that's a much bigger problem than it sounds like, because it means one of 2 things. Either there's some unaccounted for measurement effect that both telescopes are somehow missing in the same way, or the standard model of cosmology, the framework underlying nearly everything we think we know about the universe's structure and history, is missing something fundamental. If the faster rate turns out to be the correct one, the math gets uncomfortable fast. A faster expansion rate means the universe reached its current size in less time than we thought. That could shave close to 1 billion years off the accepted age of the cosmos. Not 13.8 billion years, something closer to 12.8 billion. An entire chapter of cosmic history compressed into less time than we assumed it took. Every timeline for galaxy formation, star formation, even the chemical evolution of the universe would need to be adjusted. This isn't a footnote. This is a foundational number, and it's shaking. If the age of the universe were the only anomaly, that would be enough to fill an entire field of research for a decade. But JWST didn't stop there. When astronomers pointed Webb at the deepest reaches of observable space, looking at light that traveled for over 13 billion years to reach us, they expected to find small, faint, still-forming galaxies, dim little smudges representing the very first steps of cosmic structure. Instead, they found monsters, massive, mature-looking galaxies existing at a point in cosmic history when, according to standard models, there simply hadn't been enough time for them to form. Alongside them, supermassive black holes, already enormous, embedded in galaxies barely a few 100 million years removed from the Big Bang. The conventional story of black hole formation goes like this. A massive star collapses, forms a relatively small black hole, and that black hole slowly grows over billions of years by consuming gas and merging with others. Slow, gradual, patient. But the black holes JWST found don't have that kind of time. They're too big, too soon. This has pushed scientists toward a stranger explanation. Some supermassive black holes may not have started small at all. They may have formed directly from the collapse of massive, dense clouds of primordial gas, skipping the stellar birth phase entirely and beginning life already enormous. It's a mechanism that was mostly theoretical until Webb's data started demanding it. Then there are the little red dots. That's the actual term astronomers use, because that's what they look like in Webb's images. Small, compact, unusually red points of light scattered through the deep field data. At first, they were a curiosity. Now they're considered one of the most important discoveries of Webb's mission. The leading explanation is that these little red dots are heavily obscured quasars. A quasar is an active supermassive black hole devouring matter so violently that it outshines entire galaxies. Normally, a quasar's light is nearly impossible to hide, but these ones appear to be wrapped in thick cocoons of gas and dust, filtering and reddening their light before it ever reaches us. If that interpretation holds, it means the early universe was hiding an enormous population of monster black holes in plain sight, disguised as faint red smudges. It also means our previous census of how many supermassive black holes existed in the early cosmos was drastically undercounting them. Here's where it gets even stranger. Some of the earliest galaxies JWST observed weren't just forming unusually fast, they were shutting down unusually fast too. Star formation requires cold gas. Take away the gas, and a galaxy stops producing new stars, essentially going dormant. Scientists have found early galaxies that appear to have done exactly that, and shockingly soon after they formed. The suspected cause: powerful galactic winds, driven by intense star formation or by those active black holes at their centers, blowing the cold gas clean out of the galaxy. Picture a newborn galaxy, barely a few 100 million years old, violently expelling the very fuel it needs to keep growing, extinguishing its own future almost as soon as it began. It's a version of galactic evolution that's faster, more violent, and far less patient than the textbook models assumed. All of this raises an uncomfortable question about where this is all heading. If dark energy, the mysterious force behind cosmic expansion, continues to dominate, the long-term forecast for the universe is bleak. Galaxies drift apart faster than light could ever bridge the distance again. Stars burn through their fuel one by one and wink out. Eventually, matter itself decays. The universe becomes cold, dark, and almost entirely empty, a state physicists call heat death. It's not a fast ending. It plays out over spans of time so vast that the current age of the universe is a rounding error by comparison. But it's the direction the evidence points, as long as dark energy keeps doing what it's been doing. Not everything Webb has found points toward the abyss. Some of it points toward something almost intimate, a visitor from outside our solar system entirely. 3I/Atlas is only the third interstellar object ever confirmed passing through our solar system. When JWST turned its instruments toward this comet, it detected methane for the first time on an object like this. That single detection is a big deal, because the chemical signature suggests 3I/Atlas formed somewhere between 10 and 12 billion years ago, in a star system with a chemical makeup different from our own. That makes this comet a physical time capsule, a frozen fragment carrying the chemical fingerprint of a planetary system that may not even exist anymore, delivered right into our own cosmic backyard. It's a rare, tangible connection to the diversity of planetary systems that have formed across the history of the galaxy. And finally, one piece of good news, grounded firmly in our own solar system. Asteroid 2024 YR had been flagged as a potential impact risk, the kind of object that keeps planetary defense teams up at night. JWST was used to track it and refine its orbital path with far greater precision than earlier observations allowed. The result: NASA has confirmed that this asteroid poses no impact risk to Earth in 2032. One less thing to worry about, thanks to the same telescope busy dismantling our assumptions about the early universe. Step back and look at everything Webb has handed us in just a few years. A confirmed crack in the expansion rate of the universe. Galaxies and black holes that arrived on the scene far too early. A hidden population of obscured quasars, disguised as faint red dots. Galaxies that lived fast and died young. A long-term future defined by cold, empty darkness. And a wandering comet carrying chemistry from a star system that formed billions of years before our sun even ignited. None of these are small anomalies. Together, they suggest the story cosmologists have been telling for decades is incomplete. Not wrong in some catastrophic throw-it-all-out way, but missing pieces. Pieces big enough that the age of the universe, the formation of black holes, and the ultimate fate of everything are all back on the table. The universe JWST is showing us is stranger, faster, and more violent in its youth than we ever modeled. And it's forcing scientists to admit something that's genuinely rare in this field. The numbers we memorized in school might need to be rewritten within our lifetimes. If this kind of discovery does something to your brain, that mix of awe and unease when you realize the universe is bigger and weirder than the textbooks let on, that's exactly what this channel is built for. Every week, we break down the newest data straight from the observatories rewriting the rulebook, and I'd rather have you here for the next one than miss it in the feed. Subscribe and turn on notifications, because the next discovery might be the one that finally settles the Hubble tension, or blows it wide open even further. And I want to know what you think. Is the universe a billion years younger than we assumed? Drop your theory in the comments. I read every single one, and some of the best explanations in this video came directly from viewers like you in a previous discussion.